Dear students, very good morning. Today we are going to see the Laplace transform of Laplace transformation of unit step function and unit impulse function. So Laplace transformation of unit step function and unit impulse function. Here you can write unit step function. Here you can write unit impulse function. Okay, both these two are related. Okay, this unit step function was invented or discovered or found by Oliver Heaviside, and this impulse function is found by Paul Dirac. So this unit step function is otherwise called as Heaviside function, and this impulse function is otherwise called as Dirac delta function. See, this Dirac is given to delta function, this Heaviside is given to the step function. Okay, now we want to define the functions. These unit step functions will be u of t in general or h of t. Here the Dirac delta function will be delta of t. Okay, some cases we will have a shift from t to t minus a. Okay, so for that we are defining the functions, since they are very useful in solving the problems in engineering. So we are going to define them first, and after that u of t. See, that is u of t minus a, that is given by 1 and 0. 1 when t greater than a and 0 when t less than a. It is also called as h of t minus a. H of t minus a, that is equal to, this is unit step function, this is Heaviside function, this is 1, 0, that is t greater than a and t less than a. Okay, you can write 0 for t less than a first and 1 for t greater than a next. Okay, whereas the Dirac delta function is given by delta of t minus a. Delta of t minus a, that is given by infinity when t equal to a and 0 when t not equal to a. Now you can easily able to understand, at t greater than a the value become 1, at t equal to a the value become infinity, at t less than a the value becomes 0. So less than a means in unit step function it is becoming 0, whereas if it is not equal to a it is becoming 0 in Heaviside function. Okay, for t greater than a it is becoming 1, and there is no discussion about t equal to a in step size in a unit step function. Okay, whereas here we are discussing that t equal to a becomes infinity. So the unit step function is given by means of, see, this is your t and this is your u of t. Okay, so if I want to write this as, this can be written as u of t equal to 1 for t greater than 0 and 0 for t less than 0. This is in the same way, this can be also written as h of t equal to 1 for t greater than 0 and for this t less than 0. So if it is so, I will have, see here it is 0. At this point I am having 0. So more than this, this is t greater than 0 and this is t less than 0. So my function will be like this. My u of t will be like this. So for all the values less than 0, this is your u of t, that is equal to 0. That is equal to 0. For t greater, at this point this is 0. For t greater than 0 means then to this point I will have this. This is t greater than 0. U of t, t greater than 0. This is u of t, t less than 0. Suppose if I want to plot this this impulse function, that is this unit function for t minus a. For t minus a, I will get like this. Okay, I will get like this. Okay, a small shift 0. Here it is a. Okay, this is t and this is h of t minus a or u of t minus a, whatever it is. Okay, this is h of, this is u of t, t greater than 0. Okay, this is also capital U of t, t less than 0. Okay, now for this I have told you, if I take h of t minus a means there is a shift for a. So if it is greater than a, you will have your values. Okay, less than a you will not have any value. Less than a you will not have any value. So this is your h of t minus a or u of t minus a for t greater than a. This is h of t minus a for t less than a. For t less than a. Okay, you don't know what is happening here. Okay, so that is I have mentioned it in dot lines. Okay, okay, see, both u of t minus h of t minus a are same. Okay, here the value is 1, here the value is 1. That is why I have plotted here. Okay, now for the Dirac delta function, the concept is little different, because it is if I want to do delta of t means it will become again infinity for t equal to 0, and it is 0 when t not equal to 0. Okay, it is like that. Okay, so naturally your plot will be like this. For Dirac delta function you will have like this. Okay, this is 0, this is t, and this is your delta of t. You will have like this. for t equal to 0 alone, you will have the infinite number of values. Okay, infinite, it will become infinity. Okay, if suppose there is infinity here, if suppose you are having infinity here, but it is not able to plot in a graph, no, since we don't know the value of infinity, it is not able to tell what is our infinity, where should be our infinity. I am assuming delta of t as delta of t in y-axis defines all the values for t. Okay, so if suppose it is infinity somewhere here, okay, I am taking this here. For all other values it is 0. For all other values it is 0. And here if it is infinity. And if it is here it is infinity. For t equal to 0 alone, you will have the value. That is, it becomes infinity. Okay, so I am going to shift this to t minus a. I am going to shift this for t minus a means I will get like I will get this. See, my graph will become, this is t and here it is a. Okay, and all the values less than this are t minus a and greater than this are t plus a. So I can also write this as t less than a, and this is t greater than a. Okay, that is t equal to a plus something, this is a minus something. Okay, okay, now here I am having the shift. So this is given by delta of t minus a. In y-axis we are having delta of t minus a. The shift is at, I shall write here, it is t greater than a, it is delta of t minus a. Okay, so the shift is here at a. So for all other values it becomes 0. See, this is 0, it is 0, it is somewhere, if it is somewhere here it is infinity means you will have the value here, and for all other values it is becoming 0. So this will be your, this is somewhat infinity. So this will be your plot, but actually it is not able to plot. This is an impossible function, but possibly very useful in engineering. Okay, so how you can relate these two? I am considering both h of t minus a and delta of t minus a under one graph. I am trying to make you to understand. This is t and this is h of t minus a, and here I am taking a, and here it is t less than a. All these are t less than a and all these are t greater than a. Okay, I am taking, see all these values are 0 till a it is 0, and after a it is 1. It is 1. Here it is, sorry, see, I am taking, this is 0, this is 1, and this is somewhat infinity. Okay, so after a it is 1. Okay, at a is, you can find the Dirac delta function. Here it is infinity, here it is infinity at a. Okay, at a. Okay, here it is infinity at a. So after t equal to a, the function becomes 0. Not only that, here you can see there is a green line. Okay, see, there is a green line coinciding with this blue line and coinciding with this. Okay, so this is your, see, this is your delta of t minus a. The blue line represents Heaviside function. The green line represents Dirac delta function. Okay, so for these two functions we are going to define the Laplace transformations. Okay, I hope you understand the unit step function and the unit impulse function very clearly. So I am going to tell you how to find Laplace transformations of these two. Okay, so before that, for the part A sections, questions may be asked like define unit step function or Heaviside function, and here question will be asked like unit impulse function or Dirac delta function or Heaviside function, or it is Dirac delta function. Okay, the definition is given by, see, the unit, you have to write definition like this: the unit step function, also called as Heaviside, Heaviside function, or Heaviside unit function, Heaviside unit function is defined as u of t minus a equal to, it is 0 and 1 for t less than a, 1 for t greater than a. It is also called as, it is also defined as, h of t minus a. It is also defined as h of t minus a. This becomes, so this is the unit step function. So this is the unit definition of unit step function at, we are defining everything for a, not for 0. So at t equal to a, because in the above you can see we have also given the unit step function for 0. See, it is for 0. It is for unit step function for t equal to 0. This is unit step function for t equal to a. Okay. Now we are going to define the Heaviside functions. For Heaviside functions we are going to define, you are going to define the Dirac delta function. So that is given by, you have to write the definition like this: the Dirac delta function or unit impulse function. The unit impulse function, sometimes it is simply called as impulse function. The impulse function, or it is happening at only one unit. Okay, it is happening at only one point. So the impulse function or unit impulse function, or the Dirac delta function, Dirac delta function is defined by or is defined at t equal to a by, you can write like that, you will define at t equal to a by delta of t minus a, and is given by delta of t minus a equal to, see here it is 0 when t not equal to a and infinity when t equal to a. Okay, such that integral minus infinity to plus infinity delta of t minus a dt equal to 1. See, this integration is meant to find the area. Whenever we are using integration means we are finding the area of something. It is the meaning of integration. So it means from infinity to plus infinity, if we integrate the Dirac delta function, we will get the area as 1. Okay, so it is what the Paul Dirac defined in 1927, I think. Not knowing the year exactly, but it was somewhat. But for his physics contribution, he has found that. Whereas the Heaviside function, it is Oliver Heaviside, found this for his operational functions related concepts, for operational calculus something. For that he has defined this Heaviside function. Okay, so these two are great contribution of the mathematicians to this world. Okay, we have to remember them for their wonderful contributions. Okay, so we have defined these two functions. Now we are going to find the Laplace transformation of both these. Okay, the Laplace transformation of both these. Okay, here it is Laplace transformation of Heaviside or unit step function. Heaviside function or Heaviside step function. Heaviside step function or unit step function. Okay, Heaviside unit function. You can simply write Heaviside function. This is Laplace transformation of Dirac delta function. Laplace transformation of here it is Laplace transformation of Dirac delta function. Dirac delta function. So what is this function is given by, the Heaviside function is given by u of t minus a equal to 0 for t less than a and 1 for t greater than a. The Dirac delta function is given by delta of t minus a equal to 0 for t not equal to a and infinity for t equal to a. So I will try to write a Laplace transform of this. So L of u of t minus a equal to, we know that L of f of t equal to integral 0 to infinity e power of minus st f of t dt. So that is the definition of dt. So here we are getting here our f of t is u of t minus a. So we will get integral 0 to infinity 0 to infinity e power of minus st, okay, u of t minus a, u of t minus a, that is our f of t into dt. So this u of t minus a is having 0 for t less than a. So you will get I can write it as for t greater than a it will become 1. So 0 to a e power of minus st, u of t minus a becomes 0 dt plus integral a to infinity e power of minus st, it is 1 into dt, that is equal to, this is 0, so integration of this is 0, so this becomes 0, then this plus this will become plus integral a to infinity e power of minus st into dt, and here you are getting integral it is e power of minus st divided by minus s, we are putting infinity and a here, e power of minus infinity minus e power of infinity into e power of minus as, okay, divided by minus s, infinity into anything will become infinity, so e power of minus infinity minus e power of minus s divided by minus s, okay, and that will give e power of minus infinity equal to 0, so 0 minus e power of minus s divided by minus s, that is equal to minus e power minus as by minus s, these two minus will get cancelled, therefore we get the L of u of t minus a, L of u of t minus a equal to e power of minus as by s. This is your unit step function. Okay. If they have asked you to find L of h of t minus a, don't get confused. It is also the same. E power of minus as by s. This is also same. This is also same. If in examination, if they have asked you to find L of h of t minus a, simply put, instead of you write everything as h. Okay, write everything as h. That is everything. Okay. Instead of you put as h in these two steps, the remaining steps are common. Okay, so both u of t minus h of t minus are same. Okay, now for Dirac delta function we have to find Laplace transform. So now coming for the Dirac delta function, we want to find the Laplace transformations for this Dirac delta function. Okay, the Laplace transformation of Dirac delta function is given by L of delta of t minus a. Okay, L of delta of t minus a equal to integral 0 to infinity e power of minus st delta of t minus a into dt. But we know that only at t equal to a there is a function, but actually this is not a function. Okay, do you see really any function having the value infinity? Actually, it is not a function. Also, it is not differentiable too, because we are having a special note. We are having a special note that, so you can also take this note also. The derivative of this unit step function is this impulse function. That is unit impulse function or Dirac delta function. Impulse function. There is a note like this. Okay, so the derivative of unit step function. See, in Dirac delta function you are having if it is a, okay, if it is a, here you will have a maximum value and all other values become 0. Okay, the entire thing becomes 0. The entire thing becomes 0 and there is a spike at A, and again you will get 0. Here is a spike. We are supposed to take, this is our infinity, so delta of t minus a. At A we will get infinity as a value. See, actually what is happening is, if you take delta of t, if you want to take delta of t, then you will get these all are 0. Here it will become spike at infinity. Here you will get 0. All this becomes 0. All this becomes 0, and there is a spike at this value. Okay, actually this is a discontinuous function because there is a discontinuity at t equal to 0 because it is continuous. Okay, and after this is continuous, but here is a break. Here is a break. Here it is continuous. Here is a sudden impulse. The impulse, you think it is like this. The impulse actually will take like 1, 2, 3, 4, 5, and at some infinity value it will be like this. It will be like this. Okay, it will be like this. Okay, so here according to calculus, they tell it as it is not a function, but it is also a function. It is special function. Also, this 0 and infinity as a function, in probability you are having a distribution for this. Okay, you are having a distribution for this. So when talking about the probability and statistics or probability dynamic process, I will briefly explain what this is in those areas. Okay, so now for you this is around is needed. The derivative of unit step function is impulse function or unit impulse function. The derivative of Heaviside function is the Dirac delta function. You have to know that. Okay, also there is a special note. That also there is special note that for any integral, without irrespective of the limits, for any integral, if you are taking delta of t minus a, actually I am writing nth order derivative of delta of t minus a, okay, into f of t dt can be written as minus 1 power n of nth order derivative of okay, f of a. That is, after finding the entire derivative, I am substituting a. Okay, so this is the general formula. So here you can see our f of t is e power minus st. So I am writing e power minus st, and our delta is having no derivative. it is not delta dash or it is not delta double s, it is simply delta. So it is zeroth order derivative. Zeroth order derivative means it is simply delta of t minus a integral delta of t minus a to its zeroth order dt equal to minus 1 power 0 into f power, what is f here? Our f is, what is our f? Our f of t is e power minus st, no? So e power, okay, I shall write it as d by d power 0 divided by dt power 0. Okay, so it is not a derivative. So if it is first order derivative means I will write d by dt. If it is second order derivative means I will write d square by dt square. Since it is zeroth order derivative, I am writing it as d power 0 by dt power 0, but there is no such writing style is there. Okay, there is no such writing style is there. Okay, so but for convenience I am writing it as d power 0 by dt power 0, d by dt, d square by dt square, d cube by dt cube respectively means first order, second order, third order. It is zeroth order derivative of e power of minus st at t equal to a. So zeroth order derivative, no? So our integral delta of t minus a e power of minus st dt will become minus 1 power 0, whatever power 0 will become 1. So you will get 1 into first order. So we are not going to differentiate it. Simply we are going to put t equal to a. So it is e power of minus sa. So for any integral this value is true. Okay. So what is our value? What is our required function? Our required function is integral 0 to infinity e power of minus st delta of t minus a dt. It is also e power of minus sa continuous e power of minus s, which implies the Laplace transformation of L of delta of t minus a, that is Laplace transformation of Dirac delta function is e power of minus s, e power of minus as. Okay, so the application of Dirac delta function. See, there is a spike at only one point a. Okay, at only one point a, which means we can apply a large force at one time. We can apply large force at one area. Okay, at a very small area you can apply large force. Think about a martial artist giving his extraordinary strength to break the brick, to smash the coconut. See, he is giving his utmost force to a particular area to break that object. Okay, if he applies his extraordinary, the too much of the infinite amount of force on the center area, only to the center part of the brick to break the brick, only to the center part of the coconut to smash that coconut. So this is the application of that Dirac delta function. In the same way, in an electrical circuit, if there is a shock, then that is also the application of Dirac delta function. Okay, now we have completed almost everything. Sometimes you may ask about what is impulse function and what are applications of impulse function may be asked. The applications of impulse functions of loading the loading the beam or shock loading the beam in a particular area. If you are loading a beam, it is application. If you are using a small if you are using your force to break anything or to smash anything, that is also the application of Dirac delta function. In the wall we can use the nail and the hammer to fix the nail on the wall. It is an application of Dirac delta function, because we are using the large energy over the nail. The force on the nail acts on the small region of the wall. It is not on the over, and it is not acting on the entire wall. Okay, so all those, or even the small electric pulse or small electric shock in an entire circuit is also the application of Dirac delta function. Okay, you have to go through all these things very clearly and carefully. Okay, these things may be initially for BS and B students, it may be asked as part A section, but knowing this is very essential. Suppose if they have asked you to find, separately asked you to find L inverse of 1, if you are asking to find L inverse of 1 using Dirac delta function. How to find it? We know that L of delta of t equal to 1. L of delta of t equal to 1, since L of delta of t minus a equal to e power of minus as. Here I can take a equal to 0, so that I will get L of delta of t equal to e power of a equal to 0 means e power of minus 0 into s. That is L of delta of t equal to 1, then e power of 0 into s is 1. So delta of t equal to, this is equal to e power 0, it will become e power 0, that is equal to 1. So this is what they have asked, L of delta of t. So I am writing L inverse of 1, delta of t equal to L inverse of 1. We know that what is L inverse of 1. So L inverse of 1 equal to delta of t. L inverse of 1 equal to delta of t. Okay, so you have to know this. Actually, in the same way, you may ask to find from this. Find L of h of t. Find L of h of t when h of t equal to 1 for t greater than a and 0 for t less than a, where a greater than or equal to 0. Okay, this may be the problem. Here also you can use L of f of t equal to inter 0 to infinity e power of minus st f of t dt, that is equal to integral 0 to a t greater than a. So e power of minus st f of t is 0 plus integral a to infinity e power of minus st e power of minus st. This is your h of t. L of h of t, this is your h of t. Okay, L of h of t equal to 0 to infinity e power minus st, L of h of t. Okay, this will become h of t. So e power minus st into your h of t value is 1 into, this is dt, 1 into dt. So we will get integral a to infinity e power of minus st into dt, which will give e power of minus st by minus s. For the limits you will get e power of minus infinity minus e power of minus as by minus s, which will give e power minus infinity is 0. So 0 minus of minus will become plus. So 0 minus e power minus as by minus s, it is equal to e power minus as by s. So L of h of t for this function you will get e power minus as by s, for e power of minus as by s. Okay, then if possible we shall discuss some more problems also. Suppose if you are asked to solve, again you may be asked to find, this may be our third problem. Again you may be asked to find that L of t into u of t minus 9. This is the problem. Okay, this is your problem, means how to find this solution. So here I am going to add t, along with this I am going to subtract 1 in, I am going to add 1 in, okay, into u of t minus 9. And now along with this I am going to change the position of brackets so that I will get L of t minus 9, okay, plus 9 into u of plus 9 into u of t minus 9, minus 9 plus 9 u of t minus 9. Okay, it is L of t minus 9 plus 9 into plus 9 L of t minus 9. Okay, this is one separate part and this is another separate part. Okay, so L of t minus 9 plus 9 is L of t minus 9 then plus 9 u of t minus 9. This will become L of t minus 9 into u of t minus 9, u of t minus 9, then plus 9, by linear property you can take 9 outside, 9 into L of, okay, for example I shall write it like this, L of 9 into u of t minus 9. So this is L of t minus 9 into u of t minus 9, by linear property it can be written as 9 into L of u of t minus 9. There is a property that L of t minus a into, okay, u of t minus a, okay, L of t minus a into u of t minus a equal to e power of at, e power of what, at e power of minus, like this, for having e power of as, e power of minus as into minus as into L of t. Okay, this is a property, L of t minus a u of t minus a equal to e power of minus as into L of t, and this is another property, this is what we have seen just now, L of u of t minus a equal to e power of minus as by s. So by that property you will get e power of minus 9s into L of t. That is L of, what is t here? See, L of t is t here. Plus 9 into this will give e power of minus, what is a here, 9s by s. So what is L of t? L of t equal 1 by s square. So we will get e power of minus 9s. L of t equal to 1 by s square is the formula. So you will get e power of minus 9s by s square plus 9 e power minus 9s by s. So this is the value of L of t u of t minus 9. So this is the application of, this is also an example problem under Heaviside function or unit step function. Okay, so go through all these videos. Any of this problem can be asked in part A. Okay, the thing is very simple. Only for part A, this section, this problem may be asked, but the concept is big. Its application is very big. As I told you that Dirac delta function will become one of the distribution in probability. Okay, in calculus it may not be considered as function, but it is a special function. Okay, that is what our Paul Dirac has found. Okay, so with great appreciation to Oliver Heaviside and Paul Dirac, we conclude our section. We conclude our this video tutorial. Okay, I hope you all enjoyed the problem. Every problem has solution. Even the function having infinity is also having solution, is what this Heaviside function, Dirac delta function, is telling to us. So there is nothing that can stop us when we are having utmost effort. That is what Dirac delta function is telling. Okay, so apply your utmost effort on a particular domain, that is called concentration. When you are preparing for mathematics examination, focus your utmost memory power, utmost your observation power, utmost your concentration power to a particular subject at one time. It will give you the big result. Okay, it will make you a successful person in life. That is what our Dirac delta function is telling. There is not always nothing. Sometimes there will be a spike. Sometimes you will settle in one particular place. That is what your Heaviside function is telling. Okay, there is no man is born in this earth and die in the same position. He will grow. He will achieve something. So for t less than a, he may be 0. For t greater than a, he will become 1. That is what the Heaviside function is telling. But at a, he will reach the spike. At least once in his lifetime, he will reach the goal. He will reach the spike. That is what Dirac delta function is telling. The Heaviside function and Dirac delta function is all about the life we are living. Okay, mathematics is the application of life, and life is the application of mathematics, is what my quote always. Okay, thank you all for having the wonderful session. By this time you are all preparing for Heaviside function and unit step function, and this video will be really helpful for you to cover those topics under Dirac delta function, Heaviside function. Thank you all for watching this video. Thank you all once again.